Hey everyone, welcome to The Explainer. I am absolutely thrilled to have you here today. We're going to dive straight into a really fascinating side of mathematics, how math deals with real-world limits, boundaries, and, those messy situations where things just aren't perfectly equal. We're breaking down Chapter 5 on linear inequalities today, and we're going to take those abstract mathematical rules and turn them into concepts you can actually see and use. So, I want you to start by asking yourself something. What actually happens when math isn't about finding that one exact perfect answer? Think about it. Imagine you're trying to manage a really strict household budget, or maybe you're calculating the absolute minimum grade you need on a final exam just to pass a class. In the real world, finding one single perfect number, that's just not reality most of the time. Usually, we're dealing with constraints, minimums, maximums, and that is exactly where inequalities step in to save the day. Here's our roadmap for this explainer. We'll start by moving beyond the equal sign, look at the language of inequalities, the golden rules of solving, visualizing the solution range, and then hit some real-world math applications. Let's get to it.
All right, Section 1, Beyond the Equal Sign, Navigating Constraints and Limits. Okay, let's dive into this. To really set the stage here, let's look at an everyday problem. Picture this. A guy named Ravi goes to the market to buy some rice, and he has exactly 200 rupees in his pocket. Now, the rice is sold in these 1 kilogram packets that cost 30 rupees each. If we use X for the number of packets he buys, we might initially try to write this out as an equation, right? 30 times X equals 200. But wait, think about it. Ravi can only buy whole packets. He can't walk up and buy a fraction of a packet. And because 200 isn't perfectly divisible by 30, he actually won't spend exactly 200 rupees. He might spend 180, sure, but he definitely cannot spend 210. And this brilliantly illustrates the shift we have to make in our thinking. We move from a strict equation on the left to an inequality on the right. 30x is strictly less than 200. It's a constraint, not an exact match.
Section 2. The language of inequalities. Translating limits into algebra. So, how do we actually talk about these constraints mathematically? Well, we need the right vocabulary to translate these real-world limits into algebra. And we basically categorize these constraints into two main buckets. First up, we have strict inequalities. These use the less than or greater than symbols. You can think of a strict inequality like an absolute brick wall. You can get super close to it, but you absolutely cannot touch it. On the flip side, we have slack inequalities. These use the less than or equal to or greater than or equal to symbols. With a slack inequality, the boundary line itself is an acceptable, completely valid answer. Knowing the difference between strict and slack is basically your very first step in decoding these problems.
Section 3, The Golden Rules of Solving, Manipulating the Math.
Now that we've got the language down, let's slow the pace down deliberately for a second. If you want to solve any inequality mystery, you absolutely need to master these fundamental tools. And what's really great about these rules is that they should feel incredibly familiar to you. Rule 1 tells us that equal numbers can be added to or subtracted from both sides of the inequality without changing a thing. Rule 2 says you can multiply or divide both sides by the same positive number. I mean, look at this. It's almost identical to how we've always solved regular linear equations. You just balance both sides. But there is a massive exception you need to watch out for. Beware the negative trapdoor. Let's look at a super simple, undeniably true statement. 3 is greater than 2. We all agree on that, right? But watch what happens if we multiply both sides by -1. If we just kept the sign the exact same, we'd be sitting there saying -3 is greater than -2, which is completely false. To make it actually true, the sign must flip to become -3 is less than -2. So here's the absolute crucial takeaway. Whenever you multiply or divide an inequality by a negative number, the inequality sign must reverse completely. It's literally the #1 place people make mistakes, so lock that rule in your memory for sure.
Section 4, Visualizing the Solution Range, the Universe of Answers.
Normally, when we solve an equation, boom, we get one neat answer, like x equals 5. Done. But in inequality, it opens up an entire universe of possibilities. And what's really interesting here is how the context changes that answer. Remember Ravi's rice problem from earlier? 30x is less than 200. Well, if we divide both sides by 30, we find x has to be less than roughly 6.66. But what exactly is x? If x represents physical packets of rice, it has to be a natural number, because obviously you can't buy negative rice. So his little universe of solutions is just 1, 2, 3, 4, 5, or 6 packets. But if this were just an abstract math problem where x is an integer,
the solution set suddenly expands infinitely backward into the negative numbers. 654, literally all the way down to negative infinity. The exact same algebraic problem has wildly different answers, depending entirely on the domain.
Now, to make sense of all these infinite possibilities, we map them out visually on a number line. It's kind of like a secret code we use to draw that invisible universe of answers. If we're dealing with a strict inequality, we use an open, unshaded circle on the boundary number, which shows we can't actually include it. If it's a slack inequality, we use a dark, filled-in circle to show, hey, that number is included. Then we just draw a bold line stretching out infinitely in one direction to represent the whole shebang, all the valid answers. It's a beautifully simple way to instantly see the boundaries.
Section 5, Real-World Math Applications. Using the tools in real life.
All right, let's see how this actually builds into real life. We're going to apply these algebraic tools to a real-world scenario. Here's a situation I'm sure many of you will find incredibly relevant. Suppose you want to get an A grade in a class, which requires an average of 90 marks or more across 5 exams. You've already taken 4, and you scored an 87, a 92, a 94, and a 95. So what do you need on that 5th exam? Step 1, we define our unknown 5th score as x. Step 2, we build the inequality. We add all 5 scores together, divide by 5 to get the average, and set that entire expression to be greater than or equal to 90. And step 3, we solve. Multiply both sides by 5, add up the scores we know, and isolate x. Doing the math reveals you need an 82 or higher on that final exam. It proves exactly what you need to score to hit your goal. No guessing required.
And hey, it's not just about grades. Consider this manufacturing problem. A chemist has 600 liters of a 12% acid solution and needs to add a 30% acid solution to it. But here's the catch. The final mixture must be more than 15% acid, but strictly less than 18% acid. This is a fantastic example of a double inequality. We are literally trapping our solution between two very strict chemical limits. By setting up an inequality for the 15% minimum on the left and another for the 18% maximum on the right, and then solving them simultaneously, the chemist finds the need to add more than 120 liters, but less than 300 liters of the new solution. That is math literally keeping the factory safe.
As the great physicist James Clerk Maxwell once said, mathematics is the art of saying many things in many different ways. I absolutely love this quote. Inequalities aren't just dry, boring rules on a chalkboard. They're simply another beautiful way that math helps us describe our reality. Even when things aren't perfectly equal, math still gives us the voice and the exact tools to figure out the boundaries. So I'm going to leave you with this final thought to ponder. From managing your monthly budget to figuring out passing grades, or maybe even mixing chemicals in a lab, you are constantly navigating limits. Now that you know the language and the golden rules, how will you apply these concepts of linear inequalities to the constraints in your own life? Keep your eyes open, and I guarantee you'll start spotting these hidden inequalities everywhere. Thank you so much for joining me in this explainer. Keep exploring, keep learning, and I'll see you next time.